So again, we start out focusing initially on the passive parts of the model, the physical interconnect, including the packaging and the discontinuities, plus the very front ends of the transmitter and the receiver. These passive portions of the link are very linear. Again, if you restrict yourself to passive electrical components, they're pretty much ideally linear. And they're generally modeled as LTI systems. Now, a couple other things we're going to ignore are the time varying nature of the channel itself due to changing temperature, the aging of those components, and so on. The assumption is that those changes occur relatively slowly compared to the symbol rate. So if you're running at these very high data rates, you're going to run, tens of billions of symbols through the channel every second. So even things like changing temperature even may occur on time frames on the order of seconds, but that's still not going to have any material impact on any group of tens of billions of symbols as they go through the channel. So in that case, we can model this passive part of the channel, this LTI part of the channel, with an LTI model H that can be represented both by its impulse response, which we're going to use the symbol lowercase h, and its frequency response uppercase h. And again, this assumption that it's LTI is really a prerequisite for modeling it with an impulse response or frequency response in this way. So we'll start with the central part of the model here, the interconnect itself, and then we'll move out from there, adding various discontinuities and termination and so on. So in high performance links, the electrical length of the interconnect is generally comparable to or even exceeding a wavelength at our frequencies of interest. So for example, if you consider a printed circuit board trace on typical materials that are used, for example, FR4 boards have a dielectric constant of around 4, a relative dielectric constant of around 4, which means that the full propagation of waves through transmission lines designed on printed circuit boards is usually at about half the speed of light, which means that, just for reference, if you're talking about a 10 gigabit per second signal, then a wavelength is on the order of only 1.5 centimeters. So it's, and certainly we're dealing with data rates even far exceeding 10 gigabits per second in modern high performance links. So wavelengths are really on the, as soon as you're talking about a trace that's a few centimeters long, even you're dealing with multiple wavelengths on the interconnect at a time. So when we're modeling, whether it's these circuit board traces, strip lines, microstrips, or in some cases we'll be dealing with cabling, coaxial cabling, for example, that's being increasingly used even over relatively short distances. In high performance systems, you have micro coaxial cables being used. So as soon as you're talking about lengths of those that are a few centimeters long, it's appropriate to use a lossy transmission line model rather than a lumped component model. So lossy transmission lines in general can be characterized by their resistance inductance, shunt conductance, and shunt capacitance per unit length. So we'll denote these quantities with uppercase R, L, G, and C. These are often sometimes called the specific resistance, specific inductance, specific conductance, and specific capacitance. That again simply refers to the values per unit length of the interconnect. In general, these quantities may be frequency dependent. So what you end up with is, for any short interval of that interconnect, you've got a series resistance given by R times the length delta X of that portion of the interconnect. Same for the inductance, it's L times delta X, and so on. Capacitance is C times delta X. And again, all those can be modeled with some frequency dependence to capture various loss mechanisms, which we'll talk about shortly. So many versions of Spice, commercial versions of Spice and other software tools can compute these specific resistance, inductance, conductance, and capacitance values as a function of frequency from known transmission line geometries and their dimensions, and from a knowledge of the materials that are used. So for example, there's a lot of software tools where you can punch in and say, okay, I'm dealing with a strip line. Here's the dimensions, the thickness of the trace, and the material, some constants about the materials that you're using, the dielectric constant, loss, tangent of the dielectric, and so on. We'll talk more about some of these constants later, and it'll just spit out these values over the frequency range that you specify. But I think it's good, even though that you can just get tools to spit these numbers out, it's good to have some background on the underlying physical mechanism so you know what to expect when you use software tools like that. Again, it's always garbage in, garbage out, so it's always good to know what kind of results you expect to see when you use a tool like that. So there's a bit of background on that. When it comes to the resistance, one important physical mechanism that causes loss in interconnect that you will want to confirm that you observe when you get these plots from whatever tool you're using is the skin effect. So the so-called skin effect causes a concentration of current along the surface of conductors at high frequencies. So basically, if there's a DC current flowing in a conductor, this is just a bar that I'm showing here in cross section. Imagine that could be like a wiring on a printed circuit board trace, or could even be an on-chip, on-die interconnect. Obviously, it's got some thickness and some width, and at DC, the current flows uniformly. It uses the whole cross-sectional volume of the conductor to carry the current. And so we usually make calculations of series resistance on that basis. We find the cross-sectional area of the conductor, and you're probably familiar with those kinds of calculations. But skin effect means that if you have very high frequency alternating currents, it turns out that most of the current flows on the periphery of that conductor. And that causes an increase in the series impedance of that conductor. Obviously, if you're using less of the cross-sectional area of the conductor, it's going to cause an increase in the resistance, but that appears only at high frequencies. It also, in fact, causes an increase in the inductance of that conductor at high frequencies. So this is typically, this may seem strange at first, but this is typically modeled with a complex valued resistance. So you've got the DC resistance of the conductor that's just based on the full cross-sectional area of it. And then you've got this additional term, 1 plus J times square root of F. Now the J, the imaginary part of this resistance, is obviously equivalent to a series inductance. But whereas inductance causes a complex impedance that increases in proportion to frequency, this skin effect term that shows up here is increasing proportional to the square root of frequency. You also get a real component here that is also increasing in proportion to the square root of frequency. So that's a clear loss mechanism there. Any real component of the series impedance gives rise to losses. And then you've got this so-called skin effect constant, this lowercase k subscript r. That's the so-called skin effect constant that is, again, a constant of proportionality that determines basically how quickly these losses increase with square root frequency. Sometimes you will see the skin effect constant, instead of being expressed in this way, it's expressed in terms of RS, an uppercase value is used with units of ohms per meter. That is basically giving you the amount of extra skin effect induced impedance at one specific reference frequency, F naught. So in that case, frequency is normalized to F naught, and then you use this uppercase RS instead. Obviously, RS and KR are related just by the reference frequency, 1 over the reference frequency square root F naught. But RS then, sometimes the RS is specified because it has a bit more of a straightforward physical interpretation. It's essentially capturing the additional skin effect induced impedance at that reference frequency F naught. So for example, F naught might be 1 gigahertz, and then RS is the number of ohms per meter extra impedance at F naught. Whereas KR is, again, it's sort of like the extra series impedance introduced at 1 hertz, which is, it's going to be a very small number basically. But the two are interchangeable. Now, the second main loss mechanism in interconnect is dielectric loss. Dielectric loss arises because quickly alternating electromagnetic fields cause dielectric materials to heat up. This is exactly the mechanism that we observe in our microwave ovens. You've got microwaves, and that's, they impinge on the dielectric material, which is the water in our chicken, and it's absorbed there. Those microwaves are absorbed there and cause some heating in the water. The same thing happens in our dielectric materials surrounding a conductor. All quickly alternating electric fields arise due to the quickly alternating voltages on the conductor, and that causes the dielectric material to heat up, and that's a source of loss. The quick question in the chat is saying, can you help me calculate the skin effect constant for a geometry? Yeah, that's coming. Okay, so you may find in various references out there different ways that dielectric losses can be modeled, but the best way that I found is to model it with an imaginary part of the permittivity of the material. Or, again, this is related to the dielectric constant of the dielectric constant of the material surrounding the insulator, basically surrounding the conductor. So whereas I mentioned before, FR4 dielectric in printed circuit boards has a dielectric constant of about 3.9 or 4, the skin effect gives rise, the dielectric loss gives rise to an imaginary term here. Instead of quoting the value of epsilon I, usually instead a loss tangent is quoted, which is the ratio, captures the ratio of the imaginary part to the real part of that dielectric constant. So you can see either this loss tangent specified, or it's more useful I find in equations to have this constant theta, which is related to the loss tangent just by a constant 2 pi. So just for reference, this loss tangent's typically a number quite a bit smaller than 1. Now, strictly speaking, theta is frequency dependent, but it's often safe and fairly accurate to assume that it's approximately constant for interconnect modeling over the frequencies of interest. That provides a good modeling. So just to give you a feel for a typical PCB dielectric, the loss tangent might be on the order of 0.0035. This number can change though, certainly for the boards used to carry very high speed connectivity. You may use a low loss material that has a little bit different real part of the dielectric constant as well, but the loss tangent may be significantly lower than this, specifically to improve the high frequency performance of it.